Welcome to the Deep Dive Lab, where we dive deep into fascinating science stories filled with surprising discoveries, unexpected twists, and thought-provoking ideas. And today, I want you to start by picturing something for me.
Okay, I'm ready.
Imagine walking into a dusty 19th century Wild West town.
Tumbleweeds at all?
Yeah, exactly. Tumbleweeds, you hear the saloon doors creaking,
Yeah.
and you walk up to the sheriff's office and you look at the wooden bounty board.
Right.
But instead of wanted posters for outlaws with names like, Billy the Kid, the bounties are for mathematical equations.
Okay.
And the reward for bringing them in, $1 million each.
It sounds like a surreal movie script, but this is an actual ongoing investigation in the mathematical world right now.
Yeah, this isn't a hypothetical scenario at all. In May of the year 2000, the Clay Mathematics Institute held this big meeting in Paris, and they announced a $7 million prize fund, which was $1 million each for 7 specific mathematical problems. And what makes this doubly strange to me is that these aren't new, obscure challenges that someone cooked up just to stump smart people.
Yeah, not at all.
These are like the structural pillars of modern science. I mean, one of them involves the Navier-Stokes equations, which we have used to model fluid dynamics since the 19th century. We use them for airplane aerodynamics, predicting weather patterns, designing pipelines.
Yeah.
Yet, mathematically, we cannot actually prove that they always work.
Right. They are completely foundational. We are relying on math that is essentially unverified at the absolute bedrock level.
Which is wild.
It is. And to really understand the gravity of this, we have to look at the context of that announcement in Paris. So the Clay Mathematics Institute, or the CMI, they deliberately chose the year 2000 to echo another historical moment.
Oh, really?
Yeah, exactly 100 years prior. So in 1900, the legendary mathematician David Hilbert delivered a famous address, also in Paris, where he listed 23 unsolved problems.
Okay, so they were kind of doing a century follow-up.
Sort of, but Hilbert's goal was to chart new territory.
Right.
He wanted to define new fields of mathematics for the 20th century.
Mm.
The CMI's goal, however, was fundamentally different from that.
How so? Because they weren't trying to invent new fields. They were just, putting a spotlight on the most stubborn roadblocks in the fields we already have?
Exactly. Their objective was to shatter this public illusion that mathematics is a finished subject that you just memorize from a textbook.
Yeah.
They wanted everyone to see that the frontier is still wide open and in many ways quite dangerous mathematically.
Okay, but let me push back on that premise for a second.
Sure.
Why put $1 million bounty on math we already know is hard? Like, if we already use the Navier-Stokes equations to build a Boeing 777 and the plane flies safely, why do we need to prove the equations to this impossible abstract standard? Isn't math just numbers on a page at some point?
Well, because the physics we observe in the real world isn't inherently guaranteed by the mathematics we use to describe it.
Wait, what do you mean?
We are making assumptions. So it's like we know how to drive a car really well, right? We use the math for engineering, but we don't actually know how the engine works on a fundamental level. Let's look at those Navier-Stokes equations as our prime example of the scientific mystery here.
Okay.
So these equations describe viscous, incompressible fluids. In reality, we expect that smooth fluid flows, like gentle breeze across a lake, they should remain smooth and predictable over time.
Right. Water doesn't just spontaneously accelerate to infinite speeds or fold in on itself. That would break the laws of physics.
Exactly. But our math doesn't actually rule that out.
Wait, really?
Really. What keeps mathematicians up at night is something called the scaling gap.
The scaling gap.
Yeah. So the Navier-Stokes equations track the velocity and pressure of a fluid over time and space. But when you scale these dynamics up or down, say zooming in on a microscopic part of the flow, the variables don't scale proportionally.
Okay, I'm trying to visualize this.
So using the standard mathematical tool for this, which is called the Luray-Hop energy estimate, the time variable scales by a factor of lambda squared, and space scales by lambda, but the energy estimate remains dimensionally flat.
Okay, break down the mechanics of that scaling gap for me. Why does time scaling by lambda squared cause the math to break?
Imagine you are zooming in on a tiny little eddy of water. Because space scales differently than time and energy in these equations, the energy within that tiny point becomes exponentially more concentrated the closer you look.
Oh, I see.
Yeah, so the mathematics allows for a scenario where in a finite amount of time, the kinetic energy at a microscopic point becomes infinitely dense.
Whoa.
The math literally points to a singularity, a moment where the breeze blowing past your face could spontaneously accelerate to infinite velocity at a microscopic point.
And because a singularity means infinite density or velocity, the equation simply stops functioning at that point. It's like a fatal error in the code of the math.
Exactly. Now, we know it doesn't happen in a physical lake, but because of that scaling gap, standard mathematical tools literally cannot prove it won't happen.
That is terrifying and fascinating.
Right. And across all 7 of these Millennium problems, spanning geometry, topology, number theory, computer science, the traditional mathematical toolkit has just hit a massive brick wall. To solve them, researchers have to invent entirely new ways of seeing the mechanics of the universe.
Okay, so let's dig into how researchers are actually trying to invent these new methods. I want to look at the investigations and the breakthroughs, maybe starting with the Birch and Swinnerton-Dyer Conjecture. Because usually when we picture mathematicians working on a 1,000-year-old problem, we picture, I don't know, chalkboards and dusty libraries.
Right, the Goodwill Hunting stereotype. But the reality of this investigation was quite different. If we go back to 1958, 2 young mathematicians, Brian Birch and Peter Swinnerton-Dyer, had rare access to the EDSci computer at Cambridge.
It was what, a primitive room-sized machine?
Yeah, massive machine, and they were using it for pure theoretical math, which was unheard of. They were using it to study elliptic curves over rational numbers.
Okay.
So an elliptic curve can be given by a simple-looking equation. It's y squared equals x cubed plus x plus b.
Okay, that sounds simple enough.
But geometrically, these curves look like a torus or a donut shape on a complex plane. And they possess this astonishing arithmetic complexity. Birch and Swinnerton-Dyer were crunching numbers to find rational points on these curves.
And to do that, they were looking at 2 completely different mathematical properties, right?
Yeah.
One is the algebraic rank, and the other is the analytic rank. So walk me through the mechanics of those 2 ranks. What are they actually measuring?
And let's start with the algebraic rank. It is fundamentally geometric. It measures the number of independent foundational rational points on the curve.
Yep.
Think of them as the fundamental building blocks. If you know these specific base points, you can use geometric operations, like drawing lines through them, to intersect the curve elsewhere to generate every other rational point on that curve. So the algebraic rank is just the count of those essential generators.
So algebraic rank is just the minimum number of geometric building blocks you need to build the shape.
Exactly.
What about the analytic rank, then?
But the analytic rank is derived from calculus and complex analysis. It comes from something called an L-series. Instead of looking at the geometry, the L-series function looks at the curve by reducing it modulo prime numbers.
Oh, boy.
Basically, it's essentially looking at how the curve behaves over different prime number fields and aggregates all that data into a massive infinite series. So the analytic rank is determined by how that complex function behaves near a specific point.
Okay, I want to make sure I have this clear in my head. So this is kind of like trying to figure out the structural integrity of a suspension bridge. The algebraic rank is like physically driving heavy trucks onto the bridge and counting how many it takes to bend the steel. Like a direct physical count.
Right.
But the analytic rank is like taking a tiny scraping of the steel, putting it under an electron microscope, analyzing the atomic lattice using chemical thermodynamics, and calculating a theoretical stress load.
That is a perfect analogy.
So there are 2 completely different domains of science.
Exactly. That captures the mechanical divide perfectly. You're using continuous, complex calculus on one side and discrete algebraic geometry on the other. And here is the shocking pattern that Birch and Swinnerton-Dyer discovered when they let the EDSAS computer run the numbers for weeks.
Yeah.
The analytic rank exactly equaled the algebraic rank. Every single time.
You're kidding. So the microscopic chemical analysis matched the physical truck count perfectly.
Perfectly. The L-series calculus and the geometric generators were giving the exact same integer answer.
That is like counting the rings of a true and finding out it perfectly matches the sequence of its genetic code. 2 completely different ways of measuring, giving the exact same answer.
Yes. And their conjecture states that this relationship holds true for all elliptic curves over rational numbers. If it's proven, it connects the deepest mechanics of calculus to the most fundamental properties of discrete geometry.
But it remains unproven.
Still unproven, sitting right there on the bounty board today.
Wow. So Birch and Swinnerton-Dyer found this unexpected bridge between 2 mathematical domains using an early computer. Let's look at another investigation that tried a different approach. Let's go back to the Navier-Stokes equations and the problem of that microscopic singularity we talked about.
Okay, yeah.
Because I know researchers Ning-On Lai and Yuzo recently published some findings where they were exploring a quote-unquote hidden symmetry in the 3D incompressible Navier-Stokes equations.
They did. And to understand why that's huge, you have to remember the Navier-Stokes equations are incredibly difficult because they are a system of nonlinear partial differential equations.
Right.
You're tracking a 3D velocity vector field, meaning fluid moving in multiple directions at once, up, down, sideways, and a scalar pressure field, and they all interact chaotically.
Sounds like a nightmare to calculate.
It is. But Lai and Zhu found that by applying a specific symmetric reduction, they could collapse this massive, complex vector system down into a single scalar semilinear heat equation.
Okay, wait. How does symmetric reduction mechanically achieve that? How do you take a chaotic 3D vector field with water moving everywhere and turn it into a single scalar value?
So symmetric reduction involves looking for invariant properties. It means finding a perspective where the fluid's behavior doesn't change even if you rotate it or translate it in space.
Right.
By enforcing these mathematical symmetries, you essentially lock certain directional variables together.
Oh, I see.
Yeah, and once they are locked, you don't need a vector field to track three independent directions anymore. The entire system simplifies down to tracking a single value, a scalar, which behaves very similarly to how heat diffuses through a solid material.
So it doesn't solve the Millennium problem outright, but it provides a completely new lens to analyze how these fluids behave, like looking at it through thermal goggles instead of regular ones.
Precisely. It gives us a new tool.
Now, we've talked about finding hidden bridges and secret symmetries, but there is one bounty that has actually been claimed.
Yes.
The Poincaré conjecture.
Ah, right. Proposed by Henri Poincaré in 1904, it deals with the topology of three-dimensional manifolds. The conjecture posited that any closed, simply connected three-dimensional manifold is topologically equivalent to a three-dimensional sphere.
Okay, so we don't need to get bogged down in the basic topological definitions of shapes here, but I really want to understand the mechanism of how this was finally solved.
Yeah.
Because the breakthrough came from a Russian mathematician named Grigory Perelman in 2002.
Yes, and what's amazing is he approached this topological problem not with standard topological tools, but with differential geometry. He utilized a mechanism called Ricci flow, which was originally introduced by Richard Hamilton.
Can you translate that to a mental image for me? Like, explain the mechanics of Ricci flow. How does it physically operate on a mathematical shape?
Think back to the heat equation we just discussed with Navier-Stokes. Ricci flow is mathematically analogous to heat diffusion, but instead of temperature evening out across, say, a metal plate, it's the metric tensor, the actual geometry of the shape that is evolving.
Oh, wow.
The Ricci flow equation takes the localized curvature at every point on an irregular, lumpy three-dimensional manifold and forces it to evolve proportional to its Ricci curvature.
Meaning the highly curved, sharp areas are forced to smooth out and flow into the flatter areas, like taking a lump of clay and slowly rubbing out all the dents.
Yes, it aggressively averages out the curvature of the space. Over time, the Ricci flow smoothly molds this abstract shape into a state of uniform, constant curvature, which, for a simply connected three-manifold, is a perfect sphere.
That sounds so elegant, but there is a catch, right?
A big catch.
Yeah.
The genius of Perelman was figuring out how to surgically handle the mathematical singularities that pop up during this process. Because sometimes the Ricci flow pinches a shape so hard it wants to break into two pieces.
Okay.
So Perelman invented a mathematical surgery to cut those pinches, cap them off smoothly, and let the flow continue.
And he proved it. He posted his proof online and then faced the gauntlet of the CMI rules, which dictate this mandatory 2-year waiting period where the global mathematical community brutally scrutinizes every single line of the work.
It was intense. Heavyweight mathematicians spent years writing entire books just to verify Perelman's surgical steps. And when it finally passed, the Clay Mathematics Institute officially offered him the $1 million prize, and the International Mathematical Union offered him the Fields Medal.
And he declined both.
He did.
He turned down $1 million and the highest honor in mathematics, stating that if his proof was correct, no other recognition was needed from a community he felt was fundamentally flawed.
Yeah, it proved that for some mathematicians, the prize is entirely irrelevant compared to the structural truth of the mathematics itself.
The drama is incredible, but I want to pivot to the implications for a minute.
Sure.
Because I want to answer the so what for a listener. Like, these sound mathematically beautiful, but what does this mean for me? How does solving these highly abstract equations change the real world? Let's start with the P versus NP problem in computer science.
Okay, so the roots of P vs. NP trace back to a 1956 letter from Kurt Gödel to John von Neumann. The core question is this. If a problem has a solution that can be quickly verified by a computer, which is NP, can that solution also be quickly found from scratch by a computer, which is P?
And the immediate danger that usually gets discussed here is cryptography. Because our entire internet security relies on the fact that multiplying two massive prime numbers together is easy, but factoring that massive result back into its original primes is incredibly hard. Factoring is NP. Verifying the factors is easy, finding them is hard. So if P equals NP, then finding the factors becomes just as fast as verifying them, and all modern encryption shatters overnight.
Right. That is the technological implication. But the societal implication goes much deeper, and it's kind of mind-bending.
How so?
If P equals NP, it means that finding a brilliant solution to a complex problem is mathematically no more difficult than recognizing one. It suggests that human creativity itself could be fully automated.
Okay, I have to challenge that premise. Verifying a math equation or cracking a password is one thing. But how does a computer mathematically verify a symphony or a novel or a cure for a disease? Art and discovery aren't just equations.
I get that, but in the context of NPP,
Yeah.
we're talking about problems where the parameters of a good solution can be strictly defined. So if you want to automate a symphony, you have to define the mathematical threshold for perfection, right? Harmonic rules, pacing algorithms, acoustic resonance constraints.
Right.
If you can define a strict set of constraints that allow a computer to rapidly verify that a piece of music meets all criteria for a masterpiece, and P equals NP, the math dictates that an algorithm can also generate that masterpiece just as rapidly. The barrier between appreciating genius and producing genius collapses.
Wow. That completely reframes the entire concept of human intelligence.
It does.
Okay, let's move to the Riemann hypothesis. Dating back to 1859, this deals with the distribution of prime numbers.
Right, so Bernardo Riemann proposed a hypothesis about the zeros of a complex function called the zeta function. If true, it means primes aren't distributed randomly. They follow a strict, hidden rhythm. The great mathematician Carl Friedrich Gauss had previously created a formula to estimate how many primes exist up to a certain number. Riemann's zeros dictate the error margin of Gauss's estimate.
And that error margin is incredibly small. It's bounded by a tight margin of x to the power of 1/2 plus epsilon. But, what does a margin of error actually mean for counting prime numbers mechanically?
It's basically like flipping a coin millions of times. You expect a 50-50 split, but there's deviation. This proves the deviations from the expected average in primes are fiercely constrained. It proves the distribution of primes is tightly controlled by an underlying law, rather than drifting wildly like a random walk.
Okay, but the real breakthrough in why this matters came decades later, right? During a chance meeting over tea between number theorist Hugh Montgomery and quantum physicist Freeman Dyson.
Yes, that is one of my favorite stories in math. So Montgomery was studying the spacing between the zeros of the Riemann zeta function.
Right.
And Montgomery mentioned to Dyson the statistical formula he had derived for how these zeros are spaced apart. And Dyson recognized the formula instantly. The spacing of the zeros in this pure number theory function exactly matched the energy eigenvalues of random Hermitian matrices.
Okay, stop right there. What is the actual mechanical link between random Hermitian matrices and prime numbers?
Okay, so Hermitian matrices are the mathematical models physicists use to describe the energy levels of heavy atomic nuclei, like the actual mechanics of quantum chaos in nuclear physics.
Oh, wow.
Yeah. The chance meeting revealed that the secret mathematical rhythm of prime numbers follows the exact same statistical distribution as the quantum energy levels inside an atom. The pure mathematics of numbers is structurally identical to the quantum physics of reality.
Which is deeply unsettling. I mean, we invented prime numbers in our heads, and they perfectly describe the atomic structure of the universe.
It gives you goosebumps when you really think about it.
It really does. And that ties directly into the final problem I want to explore, the Yang-Mills and mass gap problem.
Yes. This is the mathematics underpinning the standard model of particle physics, which describes electromagnetism, the strong nuclear force, and the weak nuclear force. We need to rigorously prove that the quantum Yang-Mills theory exists on four-dimensional Euclidean space, which is R4, and that it has a mass gap greater than zero.
Mechanically, for those of us who aren't quantum physicists, what is a mass gap?
In quantum field theory, the mass gap is the difference in energy between the vacuum state, so absolute zero energy, and the lightest possible particle in that field. For the strong nuclear force to operate only at a very short range, like holding protons and neutrons together inside a nucleus, the force-carrying particles must have mass.
Because if the mass gap was zero, the strong nuclear force would have an infinite range, like electromagnetism or gravity.
Exactly. And the physical reality we observe dictates that the strong force has a short range. If it didn't, the universe as we know it wouldn't exist. But the mathematical framework of Yang-Mills hasn't been rigorously proven to mandate this mass gap from scratch. Without this proof, we cannot mathematically explain why the elementary particles that make up our bodies and our planet possess the masses and interactions they do.
Wait, so we know from physical experiments that the mass gap exists, but our equations can't generate it on their own.
That's it, exactly.
We are essentially composed of matter whose mathematical foundation we cannot fully prove yet.
Yes, our existence is a mathematical mystery.
We've covered a tremendous amount of ground here, so I want to distill this down to 3 key takeaways for you, the listener, to keep in mind. Number 1, the CMI Millennium Problems fundamentally changed how the public sees math. Not as a finished textbook, but as a wild, open frontier. The bedrock equations of our modern world still have these profound blind spots.
Definitely. And number 2, progress requires entirely new ways of thinking. Whether it is using 1958 EDSAT computers to map elliptic curves, or finding hidden symmetries in fluid dynamics to turn them into heat equations, breakthroughs demand that we merge completely different fields of science.
Right. And number 3, the implications of these abstract equations ripple directly into our daily lives. They dictate internet security, our understanding of turbulence, and the physics of the universe itself. The million-dollar bounties are just bait to get us to decode the fabric of reality.
Beautifully said.
Which brings me back to our starting image, the bounty board in the dusty town. The $1 million pinned next to Navier-Stokes, or P versus NP. The money is just the bait. The real prize is the foundational code of reality. And it leaves me with this thought for you to mull over or explore on your own. If the secrets to automating human creativity and understanding quantum chaos are currently hiding inside unsolved mathematical equations, what other physical realities are just waiting for someone to write down the right formula? Are we simply inventing mathematics as a tool to describe the universe, or is mathematics an inherent physical property of the universe that we are just slowly discovering?
That is the ultimate question.
It really is. Well, thank you so much for joining us on this deep dive into the Millennium Prize problems. If you enjoyed this journey to the edge of human knowledge, please follow and subscribe so you never miss an expedition. See you next time.